Hey everyone, welcome to this explainer. Look, if you've ever felt totally bogged down by the dense math in quantum mechanics, trust me, you are in the exact right place today. We're going to completely demystify quantum gates. The goal here is to strip away all that confusing algebra and focus literally just on what you need to know, transforming those heavy equations into clear visual concepts. So let's just jump right in.
Okay, let's dive into our roadmap for this masterclass. We'll start with the rules of the quantum game, then enter the Bloch sphere, hit the Pauli building blocks, check out Hadamard, the superposition superstar, do some fine-tuning with S&T, and finally, wrap it up with your quantum cheat sheet.
All right, part 1, rules of the quantum game.
So, the absolute, non-negotiable, fundamental principle of any quantum gate is that it has to be a unitary matrix. Now, I know the mathematical condition, U dagger times U equals the identity matrix, might look a bit, well, abstract on paper. But what does that actually mean for us in practice? It's actually pretty beautiful. This one single condition guarantees two massive things. It ensures our probabilities will always sum to exactly 1, and it guarantees that there is absolutely zero information loss. Think about your standard classical computing for a second. Classical gates, like an AND or an OR gate, they're irreversible. Like, if I tell you the output of an AND gate is 0, you can't tell me for sure what the inputs were, right? That information is just gone. Poof. Quantum gates, on the flip side, are totally reversible by construction. At its absolute core, applying a quantum gate is really just reversible matrix vector multiplication. You can always hit undo and go backward.
Moving right along to part 2, enter the Bloch sphere. Okay, before we even touch the actual gates, you really need to lock in this mental model. Think of this as our game board. Every possible single-qubit pure state is literally just a point on this 3D unit sphere. It's actually super intuitive once you see it. The North Pole, that's our 0 state. South Pole is our 1 state. Out on the positive x-axis, we've got the plus state, and the negative x-axis holds the minus state. And then the y-axis maps our imaginary states, plus n minus I. So every state you can possibly compute just lives somewhere on the surface of the sphere. It takes all that complex math and turns it into simple geography.
Now, what's really interesting about this geometric view, and honestly, this is a total game changer for exams, is how it simplifies everything. Forget the intimidating matrices for just a second. Every single quantum gate is simply a rotation of the sphere. That's it. If you know what axis you're rotating around, and by what angle, you know absolutely everything about that gate.
All right, part 3, the Pauli building blocks. Let's meet the essential players.
First up, we've got Pauli X, which is pretty widely known as the quantum NOT gate. Just like your standard classical NOT gate, it swaps 0 and 1. But visually on our Bloch sphere, this is a complete pi rotation, so exactly 180 degrees, straight around the x-axis. So the North Pole flips all the way down to the South Pole. South flips up to the North. And naturally, anything already sitting right on the x-axis just stays exactly where it is. Next on the roster is the Pauli Y gate. This one is a 180-degree rotation around the y-axis. Computationally, though, it's really fascinating because it flips the bit and introduces an imaginary phase factor at the same time. Here's a massive pro tip for your exams. Memorize the relationship y equals I times x times z. It's essentially this brilliant combo of a bit flip and a phase flip, all multiplied by that extra imaginary unit. And rounding out the trio, we have Pauli Z, the phase flip gate. You guessed it, this is a 180-degree rotation, but this time around the z-axis. Now, because the 0 state is sitting directly on the z-axis way up at the North Pole, the z-gate actually leaves 0 completely untouched. It just spins it in place. But for the 1 state down at the South Pole, it flips the sign, mapping it straight to -1. Okay, I need you to pay very close attention to this next part, because this is a classic absolute trap on exams. When z acts on the 1 state and spits out a -1 state, that minus sign is what we call a global phase. Now, on its own, if the system is just in state 1, that minus sign has absolutely no physical meaning. Like, you literally cannot measure it. But, and this is a big but, if you're in a superposition of 0 and 1, that minus sign becomes a relative phase between the components. Suddenly, it is physically meaningful and will completely change how your qubit interferes and measures in other bases. Do not get caught on that.
Okay, let's move to part 4, Hadamard, the superposition superstar. I want you to think about this for a second. If you have a qubit sitting firmly at the North Pole, meaning you have absolute certainty that it's 0, how do you thrust that into a state of perfect uncertainty? How do we actually create superposition? Well, the answer is the Hadamard gate. This is arguably the single most important gate in all of quantum computing.
Conceptually, what it does is it swaps the computational north-south basis, 0 and 1, with the diagonal left-right basis of plus and minus. Geometrically on our sphere, it's a 180-degree rotation, but around an axis perfectly halfway between x and z. So it literally takes the absolute certainty of the North Pole and drops it right onto the equator at the positive x-axis, perfectly balancing the probabilities. It's just brilliant. Let's actually see how this builds into an incredible mathematical property. What happens if we apply Hadamard twice? Well, when you multiply the H matrix by itself, those 1/√2 factors pull out to become exactly a half. The interior matrix multiplication perfectly cancels the negatives out to give us 2 and 0 on the diagonals. Multiply by that half from earlier, and boom, we're left with the identity matrix, meaning Hadamard is its own inverse. Applying it creates your superposition, and applying it again perfectly undoes it.
Section 5. Fine-tuning with S and T.
So far, we've really just dealt with these large, sweeping 180-degree rotations. But real, complex algorithms, they require some delicate precision. Enter the S and T gates. You can basically think of these as fractional Z gates. Remember, the Z gate was a half turn around the Z axis. The S gate is exactly half of that, a pi/2 rotation, or just a 90-degree quarter turn. Meaning if you apply S twice, you get Z. The T gate takes this logic even further. It's a pi/4 rotation, a 45-degree eighth turn around the Z axis. Apply T twice, and you get S.
Which actually brings us to a beautiful, very clean number 8. Because the T gate is an eighth of a full rotation, it takes exactly 8 applications of the T gate to bring the state all the way back around to the identity matrix. Just a super fun mathematical fact to keep in your back pocket.
And finally, Section 6, your quantum cheat sheet.
So the crucial point here, the ultimate takeaway you'll want to mentally lock in, is this master cheat sheet. It synthesizes everything we've just mapped out: the matrices, how they transform the 0 and 1 basis states, and their geometric rotation on the Bloch sphere. Whether it's the X gate acting as your quantum knot, the Z gate flipping the phase, or the S gate acting as the square root of Z. This synthesis right here is the mental anchor you're going to need for literally any exam or algorithm you tackle. And hey, there's a very specific reason we made sure to include that tiny T gate on the cheat sheet. It turns out the T gate is the missing puzzle piece for universal quantum computation. Seriously, if you have the Hadamard gate, a 2-qubit C0 gate, and the T gate, you can approximate absolutely any quantum computation to arbitrary precision. It's crazy, but everything we've talked about builds directly to this moment.
Which leaves us with this final thought. I mean, we started today with just seemingly simple matrix multiplications and some basic geometry on a sphere, right? Yet armed with just 3 specific gates, you have the theoretical power to run literally any quantum algorithm in existence. So if an entire universe of complex computation can be built on such an elegant, compact foundation, what limits actually remain for what we can calculate in the future? Keep that in mind as you continue your quantum journey. Thanks so much for joining me on this explainer, and stay focused out there.